All right, I want to introduce the method of partial fractions. It's just a type of integral where you have a quadratic in the denominator. So, we've looked at lots of different types of integrals, and this is one that happens to, this is a method that happens to work if you have a quadratic in the denominator in the inside the integral. So let me just give you an example. So let's just say we had something like this 1 over x minus 2 times x minus 3 dx. Sometimes you'll see this foiled out where it's, x squared minus 5x plus 6 or something like that instead. But so sometimes the first step you have to factor. And there's reasons why, but it turns out right now, just looking at it this way, there's no obvious solution path that uses a technique we've used before, right? There's no substitution isn't really going to work because you're still going to have the quadratic in the denominator no matter what. Yeah, it's not clear what to use. So it turns out you use this sort of algebra. It's kind of a trick, but it's interesting that it actually works. So it turns out, let me just sort of write this down and then I'll talk about it a little bit. It turns out we can write this expression inside the integral 1 over x minus 2 times x minus 3 as a fraction, as a sum of two fractions, one which just has x minus 2 and one which just has x minus 3 for some proper choice of a and b. I'll just say for some well-chosen a and b. And this might not be obvious that we can actually always do this. It sort of didn't matter even what the numbers were down here, like the 2 and the 3. We can always find, I mean, obviously it mattered, that affects what the actual choice of a and b are, but no matter what these numbers are, we can always solve and find an a and b. And the reason why you might expect this, first off, it does some nice things. Like if we wanted to integrate this, that means we just have to integrate this and integrate this. And there should be dx's in there, but you know what I mean? We can integrate this and integrate that, and those are actually much easier to integrate, right? Because those are just natural log integrals. So that's the first thing to be aware of. So that's why it's going to be helpful, right? The second thing is like, why do we expect this? Well, let's just think about it. Let's write it out. Let's write out the right-hand side of this. So a over x minus 2 plus b over x minus 3, if you get a common denominator, right, you're going to multiply the top and bottom of this by x minus 3 and multiply the top and bottom of this by x minus 2. So it's going to turn into a times x minus 2 plus b times x minus 3 over x minus 2 times x minus 3. So if we do combine them, we get the same denominator that we had here. And now it's just a matter of making the numerator equal to 1. So set a times x minus 2 plus b. Wait, did I? Oh, this is a typo. I'm sorry. This one should have been x minus 3 right there, and that should have been x minus 2, right? Sorry about that. Right, this term we multiply by x minus 3 over x minus 3. So this should pick up like, that's this term. And this we multiply by x minus 2 times x minus 2 over, multiply this by x minus 2 over x minus 2, which is that term right there. And then I just combine the numerators. Okay, sorry about that. Felt like something was wrong. So let me fix that here, x minus 3, okay. So set this equal to 1, okay? I'll show you two ways to find a and b. And again, it's still not even obvious why there should be an a and a b, but two methods. Let me give you two methods. I like the second method more, but the first method kind of gives you a better sense of why this is true, or why you can find the A and B. If we rearrange, right, we really have AX plus BX. So that's A plus B times X. And then we have, right, that was just AX plus BX there. And then we also have minus 3A and minus 2B, right? So that's plus negative 3A minus 2B equals 1. And so that means really, if we want this to be true, X is a variable, right? This X here is a variable. So really what I want is I want this term in front of it to be 0, because that means this term with the variable goes away. There's no variable on this side of the equation. You could think of this being like something like 0x plus 1. If I could write, it would be 0x plus 1, 0x plus 1, like that, right? And so it's almost like saying, well, this should be 0 and this should be 1. Okay, so that implies, right, so this implies A plus B has to equal 0 and minus 3A minus 2B equals 1. And that's two equations and two variables which you can solve. Let me say it this way. Yeah. Two equations, two variables. It's a system of two equations, right? Solve. And you can solve and figure out, it's not that hard, right? If you just sort of say, well, this means B is negative A, right? If I subtract the A or the B over here, and then plug that in there, you get an equation involving just A, you can solve. Okay, but I want to show this other method, which I like better and is faster. So the second method is, let me write this again, this equation, and say, this is supposed to be true. You're not solving for X in this equation. This is supposed to be true for all X, for all choices of X, right? So this is supposed to be true for all choices of X, right? If it's an algebraic equation, if it's an algebraic identity, then I can, that's the whole point of X is it's a variable and it could stand for any number. And so whatever number we plug in, this equation, we should be able to pick A and B. We sort of convinced ourselves up here that you can pick A and B that would make this true, make this be 0 and this be 1. And then in that case, it doesn't matter what X is because I'm always going to be multiplying it by 0, so it's always going to go away, right? That's what I mean by this is supposed to be true for all choices of X. So let's make some good choices. So pick convenient X. Pick convenient X values. For example, think about what happens if we made X equal to 3. That term would go away, right? This would just go to 0. So, for example, X equals 3. Plug it in. A times 3 minus 3 plus B times 3 minus 2 equals 1. This term goes away. A times 0. This becomes 1. And so we actually just get B equals 1. So I immediately found B to be equal to 1. And then you can guess the other convenient value is X equals 2 to make the second term go away. And so we get A times 2 minus 3 plus B times 2 minus 2 equals 1. Now the second term goes away. This is a negative 1. So that gives you negative A equals 1, which gives you A equals negative 1. Right? And so there you go. We found our two numbers, 1 and negative 1. Right. you could check, by the way, up here, right? A and B are supposed to be opposites from this equation, which is true. 1 and -1 are opposites. Okay, if you plug in 1 there and -1 there, oops, sorry. If you plug in -1 there and 1 there, -1 for A, 1 for B, that's actually good, right? The -1 makes this a +3. The 1 makes this a -2. So you get 3 minus 2 equals 1. Okay, that works. So I like the second method. You could have done this with the first method. I like the second method better. It's just faster. It's convenient. So what we have is 1 over, let me make sure I write it the same way as last time, x minus 2 times x minus 3 equals -1 over x minus 2 plus 1 over x minus 3. And then you can integrate, right? Then the integral of dx over x minus 2 times x minus 3 is the integral, I guess it's negative dx over x minus 2 plus the integral of dx over x minus 3. Remember, by the way, I could move the dx in and out of the numerator. I could really think it was 1 and then put the dx over here. I'm just writing this for convenience sake. But the first one is just minus the natural log of x minus 2. And the second one is the natural log of x minus 3 plus c, and we're done. That's it. Okay, so that's the idea. There are certainly harder examples. You can actually do this for any polynomial on the bottom. I could have a much more complicated polynomial down here. I can even have a polynomial in the numerator. You can get really deep into this. There's like, if the polynomial in the numerator, right, it could have had like 2x plus 3 here. That wouldn't have been that bad, especially if you compare it to like, that would have just made this equation different, would have made this 2 and this 3, right? So I could have done stuff like that. But I could even make the bottom much more complicated because you can always factor a polynomial into linear and quadratic factors. And it turns out there's always a version of this partial fractions that works. It's more complicated. It's harder to see why it works. But it's possible if you ever have any polynomial on the bottom to factor it into linear and quadratic factors, then use partial fractions to get it as an integral of just functions that just have linear or quadratic factors on the bottom. And then we have other techniques to deal with those, right? So, so yeah. So that's, but we're not going to go into all that here. Some courses, if you really want to, you can try to go deeply into that, but just wanted to show you the basic idea. Okay, I think that means I will stop. If it will let me stop. Stop recording.